Right, so we're gonna first finish talking the material we were at last time. That is the part about, what was it again? It was about the utility, right? I think we have a couple of more utility measures, the analysis specific utility measures, I think, that we didn't get to finish last time. So we're gonna finish that first. And then we will have the chance to talk about part of the risk evaluations that I asked you to try, and then I posted my slides earlier today. And we can go through that. And then in the end, I'm hoping at least like 40 minutes-ish to hear from each group or each of you about how you're taking on your project. Okay, so last time we were here. So in a sense that we're trying to figure out the combining rules to get the valid inference for fully synthetic data. Okay. But then there was one thing that was new, because back then we didn't talk about how to generate fully synthetic data. So we talked about you can do full synthesis, you can do sequential synthesis, but we never demoed in class how you can do it in practice. So for the combining rules for fully synthetic data, we took the time to figure out, well, if I have two variables in the CD sample, the log expenditure and the log income, and then I'm doing it sequentially in a sense that I'm first trying to synthesize log expenditure from a normal synthesis model. So that is the new thing in this thing. And then we do the synthesis of the log income from the previously developed Bayesian simple linear regression. Okay, so the caveat we know is that, so first of all, we have to develop a new model. And in this case, it's a univariate normal model that we have for log expenditure. We didn't use any covariates or predictors, okay, just by itself. So what we do is we build a normal model on it, and then we estimate, we give weakly informative priors for mu and sigma squared, and then go from there. So everything still goes pretty similarly as before. So then don't forget that you have to, in this way, I wrote a function and also differentiate the synthesized function from before. So now I have this log exp to represent that I'm trying to synthesize log expenditure only here. So I wrote this function, and then you can do that as before. And then specifically now we have the synthesized log expenditure. And so the key that we were at last time is here on this slide, that now I have my synthetic log expenditure. But when you build your synthesis model for log income given log expenditure, that should still be on the original data. Okay, so we have done all of that, and I rewrote the name of the function here from before. So we differentiate the synthesized log expenditure and synthesized log inc. This is for the normal, from the normal synthesis model. And this is from the simple linear regression model, linear regression synthesis model, okay? So the new thing here from before is that now we have our synthetic log expenditure, right? And then we should use this, we should use this as what we fit in the second function here. Okay? Because we know that a sequential synthesis, what we do is that you synthesize the first variable first, okay, from whatever model that you develop, and then you use that to synthesize your second variable. Okay? And whenever you're building your synthesis models, in this case, we have two synthesis models, right? One for the univariate log expenditure, the other one is for the conditional simple linear regression type of synthesis of log income given log expenditure. So both of the two models should be developed based on the original data. Okay? But when you do the synthesis, especially the sequential case here, that when you're trying to get your synthetic log income, you should use the just synthesized log expenditure that you did from the previous step to do the synthesis. So that's what we mean by sequential. Okay? You build models sequentially, and then you build models based on original data. But when you're doing synthesis, you have to make sure that whatever you just synthesized should go into the next synthesis step. This is in some way a little bit similar to Gibbs sampler. You know that in Gibbs sampler we we have multiple parameters, and then you update one set of parameter. For the next one, you have to use the one that you just updated. Okay, so this is similar. And I'm sure if you're synthesizing multiple variables for a project, if you are doing the sequential approach, then this will come into play for sure. So be careful about how you're writing the code, and then making sure that you develop the model, get the parameter estimates on the original data, but then when you do synthesis, you're synthesizing based on the synthetic data. So to get a little bit more abstract here, say I think I'm generating 20 synthetic data sets. I have my M equals to 20, and then I have this list, synthetic M, to save all of the synthetic data. But I prepared this slide just to re-emphasize the point again. So notice that each data set is generated using one of the last independent MCMC iterations. Okay, so that's what we did. I mean, the code that I wrote, that's what it was doing. But notice that we have two models. Okay? We have the Bayesian, we have the model 1, we have the normal model, or log expenditure, right? Model 2, we have the simple linear regression of log income given log expenditure. Okay, so you notice that when we are getting one set of synthetic data for both of the two variables, the way that I did it is I'm using, say, for example, I think because I'm using the last 20 independent draws. So what I was doing is I think I was using the 4,981st iteration from this, right? And then I use the same corresponding iteration in this, and I'm combining them together in some way, right? But this is arbitrary. What I'm trying to say is, if you have, so down here in the last bullet point, if I have my, let's just say 2 variables, A and B, okay? And I have a model for A, and I have a model for B of B given A. That's essentially what we're doing, okay? What I want to get the idea that I want to get across here is that, say, for my A variable, I generate synthetic versions of it, right? Let's just say I get weight A1, A2, and A3. We add the star just to make sure that they are the synthetic values. They're from their model, okay? From whatever iteration you do. Okay? And now we know that we have to use the synthetic A values to generate the synthetic B values. Okay? But then we know that because we have 2 separate MCMC. Okay? We have 2 separate models. So you have like different iterations, different sets of iterations from the 2 models. So how can you pair them up? I mean, that's a natural question. If I have the last 20 from my first model, the last 20 from my second model, should I just do like the first go to the first, the second go to the second, and the 20th go to the 20th? So that is totally up to you, because, well, they're all independent from each other, okay? The goal is that when you're doing a B star, say I'm trying to get my, so the example here I'm giving is, well, I might want to get my first set of B, even the second set of A, which is totally fine, okay? But you can also get the first set of B to get the first set of, from the first set of A, or if you want, to get the first set of B, given the third set of A, okay? So what we mean by this is that, well, we have 3 different, 2 sets of 3 sets, okay? But within, like, between this A1s, A2, A3, they're all independent from each other, okay? And the models that we develop for B given A, each iterations that we're going to use, they are independent across each other as well, okay? So that means as long as the 2 MCMC, first one and the second one here, both of these are converged, and the parameter draws that you get from them, they're independent from each other, then how do you do the pairing doesn't really matter, because they're independent from each other. What we're trying to do is we generate A first, and then from A, I want to get B. Okay? So once you have converged independent draws, which pair you're using doesn't matter. Okay? There will be variability, of course, because once you do a different set of the pair, you will get a different set of results, but that wouldn't change the whole picture. Okay. So that's why I mean, so from the previous slide, you see that the way that I'm doing it as a demo is I'm doing it like at the same iteration. Okay. It is corresponding to each other, but it doesn't have to be in this way. All of the MCMC, they are independent now, they're converged, they're independent from each other, so you can use any kind of pair. But you shouldn't do, I mean, like say, for example, if I'm now having my A1, A2, A3, the star versions, because now I have all of them synthetic, then when you do B1, you can use like one of the A's, let's just say you use A2, but then the next one you shouldn't use A2 anymore. You don't want to redo it. I mean, again, you're trying to capture all of the variability that you introduce into the model. Okay? So that means, well, I have my A1 through A3, all of the star version, so I should use all of them, but I don't duplicate. But you can do any kind of pairing between the A and B from now on. So a quick way to do this, I mean, I sort of picked the simplest way, well, just to use the same, in the sense that corresponding iteration, so I don't make mistakes. But what we're trying to convey here is that the pairing doesn't really matter, they're all independent, and the sequential manner requires us to develop our models on the original data set, but then when we're doing synthesizing, we have to synthesize the next variable using the one that I just synthesized. Make sense? So maybe a quick question to ask you. So how many variables you are synthesizing for your project? Anybody just did one? You can just raise your hand.
Oh, just input.
Okay, so in that case, you wouldn't deal with the sequential stuff. Okay, that's fine. Anybody did two? Or trying to do two? Like, what are the nature of the variables?
Well, it's geographic, so it's longitude and latitude.
Okay. So you're synthesizing both of them. Okay, so both of them, I guess, will be continuous. Okay, so and you are trying to do a sequential?
Yeah.
Okay, okay. Yeah, all right, so in that, oh, it's not an easy task. I mean, yeah, so it's geographic. It's definitely not something easy to do, especially if you think about the longitude and latitude, even though they're continuous, but they're not continuous in the general sense that we think about. Right? Okay, but okay, so you're doing two, so then in that case, I mean, the pairing and how you're doing it, I mean, you would do it sequentially and then go from there. Okay. Anybody else did two? So everybody else did three or more? Maggie?
Yeah, we did multiple,
Mm-hmm.
and I kind of, because I was dealing with political ideology data sets, and I first synthesized sex, try to synthesize race and age, doing them separately, and then use these three synthesized variables to synthesize income, and like I was using these three to synthesize education, and then use these four to synthesize income, and then use all of them to synthesize your political ideology.
I see. So there is, I mean, certain hierarchy, like how you're doing this, yeah. So that would be the case, like you say, you have at least 4 or 5 variables, and then in that case, you would dealing with make sure that like all the pairings will make sense. And Chad?
Me and Isaac are using, I think, like age, sex, and gender to synthesize first highest degree earned.
So age and sex, they are unsynthesized.
Yeah. We're gonna,
Okay. So you're using it to do what was it? What was the variable you were synthesizing?
highest degree earned.
Okay. Degree. Okay.
And then using all of those, trying to figure out like what type of employment.
Okay. So all of this, well, age will be continuous, I guess.
Yeah.
Okay.
And also race.
Oh yeah.
In the first one.
Okay.
And then we're gonna use everything to synthesize salary.
Oh, I see. Okay. So race here, and then everything here to go to salary. Okay. All right. Yeah. So again, I think there was certain sequential happening here, like you're using the 3 for degree, and then when you're combining degree and the other 3 to get to employment, then there will be the pairing, and then lastly with the salary. Okay, so there is a sequential approach here, and then the pairing will will definitely play a role. Ray?
Oh, I did one.
You want, okay, all right, yeah, that's an easy, well, no, I mean, not only I'm just saying that, then you wouldn't have to do too much with the sequential, but if you're doing more than one, definitely make sure that you know how the pairing is working. And again, there's no fixed order of the pairing. Any one is fine, just don't duplicate what you use. And then make sure that you use the converged iterations and then doing that sequentially. All right, so, okay, so, but coming back to the combining rules, I mean, for this part of the lecture, we're trying to make sure that we know how to do combining rules for fully synthetic data, okay? And then for the partially synthetic data, I think I was using like the mean estimate for one of the variables. For this one, let's think about a regression type of estimate, okay? So the regression that I'm thinking about here is looking at log income from like conditioning, I mean, a regression analysis from the log expenditure. So what we're doing here is, in fact, I mean, if you look at equation 12, this is exactly one of the regression, one of the synthesis models, right? We're using the synthesis model to synthesize log income, right? But we can also think of this as a utility measure, and then in particular, this is an analysis-specific utility measure, so we have to use the correct combining rules. And in this case, we're focusing on this beta 1. Okay. So unlike what we did for the mean case, because for the mean, you just get for each synthetic data set, you get the mean, you get the variance, and you get the computation and all that. When you're doing regression type of work, well, when you're getting the mean, the point estimate and the standard error of those estimates, you can just use it from, I mean, the output from the LM function. Okay, because that's at the end of the day what kind of regression type of work that you're doing. So if our goal is this beta 1, then what you do, step 1, to do this combining rules, is that you compute your QI and VI, the point estimate and the variance estimate of the regression coefficient. And then to do this, you do LM function to perform the regression analysis on each synthetic data set, right? And then you get your QI. Okay, so I think I wrote a function to obtain the QI and VI. Looks a little bit more complicated, but really I was trying to label all of the variable, I mean, all of the parameters with betas, beta 1. That's why you see like a lot of text, but you can also simply name them as Q and V, and then you will save a lot of space. But pretty much you notice that because we have to loop this through and synthetic data sets, right? Because we have to do the regression analysis on each synthetic data set and then get my Q and my V. So you should do a loop, and looping through 1 to n. Okay? And then what you do is you get the synthetic data, the I of them, around the linear model, which is LM, log income, regressed on log expenditure. The data set is the data synthetic data I that I just grabbed from my synthetic data list. And then you can do a coefficient output. And in particular, this is just, well, once you show your output, you will notice that in order to get the variance, in order to get the point estimate and the variance, you have to get that indexes right. So this is just from the output, and you will know what it is once you run it. Okay, because when you do this kind of regression, you have the beta 0 and beta 1, right? You have the 2 estimates here. So that's why you have to, I think, always have to get to the second row, because that is the row corresponding to the slope in the output. And then they will give you the first entry to be the point estimate. The second entry is the standard error. Okay. So keep in mind that B is the variance. Okay, so you have to square the standard error. So that's why there's this square 2 over here. Make sense? Sense? Okay. And then you return this, and then so this is how I wrote this function, and then you can just get your Q and V from the output. Make sense? No? Okay. So that's the first step. You get the Q and V, and the second, we know that we have to get the Q bar, V bar, and V bar n. Okay, so that is taking the mean of the Q's, taking the variance of the Q's, and then taking the mean of the V. Okay, this is very similar as before. Third, we have to get the variance estimate. So the first one to do is this 1 plus 1 over m times bm minus v bar m. And unfortunately, when you do this, you realize this becomes negative. Okay, we shouldn't have a negative variance. So in that case, you would just use the other alternative non-negative variance that we talked about earlier. And what you do, well, pretty much it will just boils down to this v bar m itself. Okay. But we're following this definition. So as you can see that we should get the max between 0 and TF. This TF is negative, so this term becomes 0, right? And then the second term here is delta times n seen divided by n times v bar n. So delta is 1 since TF is 0, smaller than 0, so this becomes 1. And this, we know that since we're doing synthetic value for each observation, so the n seen becomes n, so this ratio becomes 1. Okay. So that's why in the end, you have this v bar m. So, but I mean, you can just code everything here. And just as I did this must be a typo, right? I should have a max, right? Right? Yeah, sorry about that. So yeah, wrong result in the end, I'm sure. But this should be the max, okay? Because the min, I mean, I think the min will take the TF, but we should have 0 here. Anyway, so this is a little bit off, I'm pretty sure, in the end. So if you did it correctly, you probably have a different answer from mine. But yeah, make sure that don't make typos like this, because this will be definitely not good. Okay, but from the definition, we know that it should be a max, not min. All right, so suppose, well, we have a refined TF nu, and then that will, all right, and also we have to get the degrees of freedom. So this, again, in R, just type in the formula carefully and make sure that, like, in this case, because there's so many parentheses going on, make sure that you get it in the right one. Well, I don't even know if I got it wrong or got it correctly, but anybody tried this and figured out anything slightly different? I mean, because I can come to the answer here. I think the point estimate, well, both of them are, well, I think the point estimate will still be fine because it's still the Q bar. Yeah, but then I'm pretty sure my, this is off because just as I typed the max wrongly as min, so this number is different from what it should be. So I think the confidence interval will be slightly different. Okay, all right. So I will update that, but make sure that when you're doing it for your project or like verify your method on the example data, make sure that you get it right. Okay. All right, so the synthetic one, well, a little bit off now, but anyway, let's just say it is right. 0.60 to 0.81. And then, okay, yeah, by the way, this will be what the output looks like. So you can always get you should always get your confidence interval from the sample, which is from the original data. So that's where you run this log, LN function on the original data, and then this was the summary. So that's why earlier we're getting the Q from here, right, and getting the V from here. Yeah, so that's what the output would look like, and that's why, well, in this case, you're able to get your point estimate as well as the point estimate is, sorry, not this one, this one. This is your point estimate for the slope. And then for your confidence interval, well, you have a t distribution here, so you have to get the t-score from this, and then multiply with the standard error, and then do plus minus to get the confidence interval. A little bit tedious, but you're definitely able to do this. So I plug in everything over here and then get a confidence interval from the original data. Okay. So even though I think my confidence interval earlier from the synthetic data is a little bit off, but wouldn't be too much off. So I think in this case, the confidence interval is not that close to the original. Okay. And this will naturally lead us to the last topic here.